Welcome to this explainer. Have you ever just stopped, looked around at the natural world, and felt totally overwhelmed by how incredibly complex it all is? From the vastness of the stars, right down to the microscopic cells in our own bodies, there is so much happening all at once. It's way too much to take in just by looking. But thankfully, we've got a way to make sense of all this chaos. Science actually gives us the ultimate toolkit, a reliable, systematic way to explore and really understand the universe we live in. So today we're going to unpack exactly what's inside that toolkit.
Think of this as our literal explorer's map for today's journey. We'll be looking at the tools of exploration, making sense of things with models, the actual language of science, the difference between laws, theories, and principles, the power of prediction, and finally, connecting the scientific world. Okay, let's dive into this toolkit together.
Kicking things off with Section 1, the tools of exploration, observation, and direction. So, when you're entering the world of secondary science, it is absolutely crucial to realize that it isn't just about memorizing a bunch of dry facts. It's a dynamic method. And our very first tool here is careful observation. Kind of like using a magnifying glass. It's about taking the time to notice hidden patterns, those really fine details, and paying close attention to the stuff that gets completely missed by the casual observer. It is quite literally the root of all discovery.
But here's the thing, observation alone just isn't enough. Our exploration has to be paired with purposeful direction. Think of a compass. We can't just wander aimlessly, right? We need to choose the appropriate models, ask the absolute right questions, and honestly, know the limits of where our ideas actually apply. Put them together, and observation and direction give our scientific exploration its true purpose.
Moving on to Section 2, making sense with models, simplifying reality. Because the real world is so incredibly complex, trying to study it in full detail is, well, practically impossible. So what do scientists do? They simplify reality. To wrap our heads around this, let's picture a totally relatable example. Imagine a cricket ball being hit high and hard for a 6. We want to build a simple model to answer one highly specific question. Will the ball cross the boundary without hitting the ground first? Now, if you were building this model, what details would you actually need to include, and what could you just toss out?
Now, what's really interesting about this slide is how we deliberately ignore things to get to the truth. To figure out if that ball crosses the boundary, the mass of the ball, the speed, and the direction it was hit, those are absolutely crucial. But the brand of the bat, the exact color of the ball, the length of the grass on the field, we completely ignore them. And ignoring those details isn't a mistake. Actually, scratch that. It's a deliberate, purposeful choice to keep the model simple enough to give us the exact answer we're looking for.
That brings us to Section 3, the language of science, precision, and mathematics. So if you want to communicate across the globe, you really can't use vague terms. Science demands precision. It uses highly specific standard units, so there's zero ambiguity no matter where in the world you are. Let me tell you a crazy story that shows exactly why the shared language matters. There's this famous incident where a massive passenger airplane literally ran out of fuel mid-flight. No way, right? Why? Well, the flight needed 22,300 kilograms of fuel, but the ground crew miscalculated. They used the density of fuel in pounds per liter instead of kilograms per liter. Because of that one simple mix-up in standard units, the plane was 15,000 liters short. Thankfully, it managed an emergency glide landing with no casualties. But man, this is exactly why the international community agrees on standard scientific units. It avoids massive errors and keeps everything safe and fair.
All right, Section 4, laws, theories, and principles. Organizing understanding.
As our measurements get refined and experiments are repeated over and over, our understanding gets grouped into 3 distinct categories that people mix up all the time. First up, a law. A scientific law describes a regular pattern observed in nature, often using math. Think about being on a city bus. When the bus stops suddenly, you feel that physical jerk throwing you forward. That predictable, repeating pattern of motion is described by Newton's laws.
Next, we have a theory. A theory goes a step further and actually explains why those patterns occur, based on a massive amount of gathered evidence. For example, the atomic theory explains exactly how molecules are formed. And please remember this, in science, a theory is never, ever just a random guess. It is a rigorously tested explanation.
Finally, a principle. Principles are these broad ideas that help us make sense of specific situations. If you're climbing a steep flight of stairs and feeling totally exhausted, well, the principle of conservation of energy helps explain the physical work you're actually doing. Laws, theories, and principles, they all work together to structure our knowledge.
Section 5, the power of prediction, testing reality.
Prediction is the absolute superpower of the scientific method. Once we have our models and our laws, we can actually anticipate the future before we even run an experiment. And these aren't wild guesses, they're reasoned expectations. Let's test this reasoning power right now with a fun mental estimation exercise. How many liters of air do you think you breathe in a single day? Sounds impossible to know off the top of your head, right? But scientific thinking breaks it down into solvable chunks. Step 1. We estimate we take about 12 to 15 breaths a minute at rest. Step 2. Multiply that by 1,440 minutes in a day, which gives us roughly 20,000 breaths. Step 3. Think of blowing up a 2-liter party balloon. It takes about 4 breaths, so 1 breath is roughly 0.5 liters. Step 4. Multiply 20,000 breaths by 0.5 liters. Boom! You breathe about 10,000 liters of air a day. That's enough to fill a small swimming pool. Science really values this kind of careful, approximate reasoning to help us build intuition and check if an answer makes sense in the real world.
Now let's point this superpower of prediction and reasoning at a viral myth. You've probably seen claims on social media stating that eating food during a solar eclipse is harmful. I want you to pause for a second and directly challenge this using your new scientific toolkit. Is there any actual evidence for this?
Well, the crucial point here is looking at the actual physics of the event. An eclipse is literally just a play of shadows. The moon is simply blocking the sun's light. Does the temperature radically change in a way that spoils your food? No. Does food go bad just because it sits in a shadow for a few minutes? Of course not. By asking simple, scientific questions, we can confidently predict and conclude that there is absolutely no physical, chemical, or biological mechanism that makes food harmful during an eclipse. It's just a shadow.
Bringing us to Section 6, Connecting the Scientific World, Interdisciplinary Approaches.
We often learn physics, chemistry, biology, and math as totally separate subjects in school. But out there in the real, natural world, those boundaries just do not exist. Solving major real-world problems requires mixing all these disciplines together into what we call an interdisciplinary approach. Let's look at one vital, everyday object that perfectly proves this. To understand and design this single object, we need physics to understand particle motion and electrostatic attraction. We need chemistry to formulate the specific polymer fibers. We need biology to understand the exact microscopic size and behavior of a virus. And we need mathematics to model the airflow and filtration efficiency. All 4 distinct branches must converge perfectly. Any guesses what it is?